All right. So I want to pick up with where we were Monday. All right. So the homework starts out with some stuff on forces. Starts out with the maglev problem. But then it gets into rotating machine stuff and it gets into specifically to synchronous generators. So I want to review and kind of finish up where we were with this thing. So the synchronous machine, generally used as a synchronous generator. This is the picture, the cross-sectional picture that I have used for this thing. Okay, so this I said is a two-pole machine. All right, now this two-pole machine, what does it mean to say that it has two poles?
The direction changes.
Yeah, the field basically, as I go around that air gap one time, the field changes direction once, I guess. I mean, the field points. So in other words, let's do coil A here. I always look at A. So what's it mean when I have the circle? What's the current doing? Coming out, and when it's X, it's going in, right? So that means if, first of all, it would go like this, right, around the air gap in that counterclockwise direction. And basically it's coming across the air gap along the top, right? So it's basically, if I were to go all the way around the air gap, it would look like that. And then it would be shooting across the air gap towards the stator on the other side, right? So it was what we said, if I plotted that as I went around, as I go from 0 to 360 degrees. Now, as I go, so 0 degrees, I got it marked out here. 0 degrees is over there, 180 is on the other side. All right, so in this case, if I do BA of theta like this, again, I'm just going to assume that I have a DC current in that winding. Which direction does the field go from 0 to 180? Yeah, it goes
Inward radially.
Inward radially. All right, you guys doing all kinds of pictures. Yeah, if I had that picture right there, this is not this would not, or this field right here, this would be if I had what I called my sinusoidally distributed windings. All right. So if I have my sinusoidally distributed windings, I would get a field strength that looked like this. If they were concentrated like I had right here, right? Concentrated meaning they were all sitting at one spot, right? Then that would basically mean I would have a square wave, right? That would be the difference. But we said we try to get them to be that way. Now, I added something in here, which I'm going to come back to here in a second. Is I said if they were sinusoidally distributed, then I use this cosine distribution, right? So this guy would be maximum at theta equals 0, and then it would go down from there. But I added this thing P over 2, because I tried to generalize this now to a machine that has what I'm saying is P poles, okay? All right, we're going to get into that in a second, but let's just go over our basics. So in this case, what I'm going to say is the rotor has an angle, theta R, which is equal to omega mt plus theta naught. What the heck does that mean? Omega mt plus theta naught. At t equal to 0, where is this thing sitting? Theta naught. All right. At theta equal to 1 revolution. So in other words, if this guy went around 1 revolution, where would it be sitting? Theta naught. Okay. So every time he goes around 1 revolution, he's sitting at theta naught. Now, the thing I did here, which I'm going to get back to here in a second, is I called this omega m. All right. So this omega m is going to be what I'm going to call the mechanical speed. All right. In other words, how fast that guy's moving in the real world. All right. We're going to get to this in a second. Now, the stator currents are what I say are 3-phase, right? Which means that those are going to be currents. They're going to be I cosine omega t minus 120, so on and so forth. And the rotor current is always DC, all right? So I put a constant current into the rotor, and then I have 3-phase currents in the stator. All right, that's our basic setup for this. Now, if I go to a machine that has more poles, this guy on the left is the 2-pole. This guy on the right is the 4-pole, okay? What do we see that's different with the 4-pole than the 2-pole, right? Well, here's A coming out, then here's the A return, with going in, right? Then there's A again, and there's A prime again. Okay, so if I were to draw the B field here, you guys correctly identified that as a function of theta, it's going to look like that. What's it going to look like for this 4-pole machine as I went around 360 degrees?
Got 2 periods, but
Yeah, the period would be cut in half and the frequency would be twice. So it would look like that. So this would be 360 degrees. This would be 180 degrees. And what we say is we say that this is the actual angle. And then we also define something that we call the electrical angle. Okay. And we say that this point, wherever I get through my first period, this would be theta E equal to 360 degrees. Right? So the way I can look at this is I can say that this thing right here is, in this particular case, you would say that this is sine of 2 theta, right? So the other way of looking at this is to say, so what we do is we can say that this is sine of theta E, where theta E is always equal to P over 2 times theta. All right, so we give it an electrical, so we talk about an electrical angle and a mechanical angle, an angle that exists in the real world and an angle that exists in the physical space. So for this particular case right here, what I say is, in general, if I have for a p-pole machine, I have this guy is P over 2 times theta. The electrical stuff is like that. What that also means typically, I'll write it here this way, is to say that we define electrical speeds, which are also related to the mechanical speeds like that. All right. Now I'm going to get into that in a minute, right? If basically what this means is that if I'm in a 60 hertz grid and I have a 2-pole machine, in a 60 hertz grid, a machine turns 60 times a second. If I have a 4-pole machine, it's going to turn at 30 times a second. All right, half of that. If it's a 6-pole machine, it's going to turn 1/3 of that. So instead of being 60 hertz, it's going to be 20 hertz. All right, and just kind of goes on like that. All right, so let's look at what that means. So this is what I've determined, or what we've kind of determined up till now. So if I have this machine, my stator currents look like this. Okay, so I want to go back and I want to remember for a second. All right, if I turn this into the phasor domain, what are these things in the phasor domain? How do I write these?
first one is I angle here.
Yeah, and I'm going to say IA over square root of 2 to get it to RMS. And I'm going to say this guy has an angle of 0 degrees. And then these guys would all be similar. IB is same magnitude with an angle of negative 120. And I want to be careful. This guy's an angle of phi, right? I tried to be specific about this, right? And there's a reason why I did phi. So this is phi minus 120. What's that? Okay. And this is going to be phi minus 240. That. All right. Now, what I did here was I wrote out, okay, well, this is what the field patterns look like for A, B, and C. Sorry, this is C, right? For A, B, and C all together, right? Now, what have I done here now? Well, the only thing that's different, right, is I put in that P over 2 to basically say that if this guy has multiple poles, right, then I have to take into account this this pole factor, I guess. All right. All right. So if I were to do this, I mean, just to say like, okay, all that says is if I had a 4-pole machine, if I went around the rotor one time, right? I went around the air gap one complete time. If I had a 4-pole machine, how many periods do I see in that field? 2 periods. If I had a 6-pole machine, I would see 3 periods. If I had a 8-pole machine, I'd see 4 periods, right? That's basically what that's suggesting. Okay. Now, if I did this together, if I look at both the rotor and the stator together, we said that I add all of those fields together. I said that if I take B sub A plus B sub B plus B sub C, it ends up being this whole thing right here. All right. B sub R is the field from the rotor. Okay. Now, when it comes to the rotor, what do we say? What kind of current's inside the rotor? DC current. So why did it have this moving field piece to it? What's that? Because of the rotation, right? So we said that the angle of the rotor is theta R, and this is an actual angle. Physical angle. Yeah, let's call it that instead. Physical. That's a better term. Physical angle, which is omega m times t plus theta naught, wherever that guy truly begins in space. So let's take a look at this. So first of all, if I sketched B sub S of theta, right? If I did this for a 2-pole machine, so let's say I had 2 poles. So P equals 2, right? What would the field strength look like in the air gap? So first of all, this would be 0 degrees. This would be 60 degrees. This would be 120 degrees. This would be 180. This would be 240. This would be 300. And this would be 360. Like that, right? So my field strength would, first of all, how do I sketch the field strength? How do I sketch this thing? Right here.
2 poles, 1 period.
It's 2 poles, so there'd be 1 period. But how do I sketch it? It's a little bit weird, right? Why is it weird? I guess that's a subjective question, but what makes it weird? Because it depends on not just theta, but it depends on what?
Space.
Well, theta is space, but it also depends on time, right? At t equal to 0, this field looks one way. At t equal to some later time, it looks a different way, right? What this is saying is that if I looked at the B field in this air gap, it would, let's see, it would point in towards the, well, it would point towards the rotor. So point towards the rotor like this, and then towards the stator, and then back to the middle, right? That's basically, if I looked at the field strength, the fact that so this would be the 0 line right here. All right, so it's pointing towards the rotor and then towards the stator. Okay, so if I'm looking at this, if I had a 4-pole machine instead, what would be different? So this would be for my P equal to 2 down here. This would still apply if I had a P equal to 4 as well, except what would the angles be? This would be what? This would be this. They'd all be half of that. So this would be 30 degrees. This would be 60, 90, 120, 150, and 180. Right? So in other words, I've gone around essentially I've gone around once electrically, but I'm only halfway around the air gap of the machine when I make it to 180 degrees. All right. I'm only halfway around the actual air gap, but I've made it around 1 electrical rotation. All right, now the thing is, this is showing the field at what time? Right, if this is my zero line right here, what time is this showing it for? T equal to what? That's a fancy expression. Sine omega t plus phi minus p over 2 theta.
T is equal to 0.
T is equal to 0, right? At t equal to 0, this is what it would look like, right? What happens as time advances? What does that field do?
The phase shift.
The field, yeah, basically phase shifts, right? Because we said what's going on is the field is moving, right? So in terms of the air gap itself, it's rotating around the air gap. It basically means from this picture here where I've kind of drawn it out lengthwise, which means that the field would move over time, just keep shifting. Okay. So how fast is this guy moving in time? So the stator field, how fast is he moving in time? Somebody other than Musa. How fast is this guy moving? So omega, right, is how fast he's moving. What is omega if I'm connected to a grid? 2 pi 60, right? Now I said this guy is called a synchronous machine. Why is he called a synchronous machine? To make a constant torque, again, I'm not deriving that, but basically I'm saying to make a constant torque, those two fields have to move at the same speed. All right. So if you look at the rotor field, what's the speed at which the rotor field is moving? I wrote it as P over 2 times omega m. All right. So if I had a two-pole machine, so P equals 2, the rotor is moving at what speed? 60 hertz. If I had a four-pole machine, what's it have to be moving at? Half the speed. All right. So this is why. So if omega m is half of omega, right, then omega electrical is P over 2 times omega m. And it's always the case that omega electrical, in the United States at least, is 2 pi 60. All right. If I was in Europe, it would be 2 pi times 50. So in order to get the stator field and the rotor field to move at the same speed, the rotor has to move at a slower speed. Now, if I went into different power plants, I'd see different speeds. Most of your big power plants, you have a two-pole machine or a four-pole machine. If I went to a hydroelectric plant, it might be a 48-pole machine or something like that. If I had a 48-pole machine, how fast is that motor moving?
60 over 40.
Very, very slow, right? 60 over 24. That's what it would be, half of that, right? But it would be moving at a pretty slow speed, all right? And usually with water, it is moving at a pretty slow speed. Okay, all right. Basic concept. We don't need to worry too much about the fields. The reason it's called a synchronous machine is those two fields move at the same speed. Okay. All right. So what I want to move on to is basically two things. So we've kind of talked about the flux, but I want to work out the flux more formally, and I want to work out the circuit model and use this thing as a generator. That's where we ended up the other day. So I want to finish up the circuit model, and I want to look at some example problems of connecting this thing as a generator. Okay. All right. So here's my basic picture. I want to try to figure out the machine fluxes. All right. So we had our basic approach to figuring out, magnetic circuit stuff, right? Where I basically, back in the magnetic circuit basic stuff, you guys would have said, like we did before, for this basic two-pole machine, I had if I looked at phase A, I got a flux doing this, right? And then I got a flux doing this, all right? Now, this approach turns out to be kind of messy when I'm talking about circular geometries like this. All right, so we're not going to worry about it too much. I want to just make sure we understand the basics. If I were to just think about phase A right there, and I say there's NS turns in A, B, and C. All right. In other words, I said they're identical, right? They're completely identical to each other. If I were to draw out a magnetic circuit for coil A, what would the magnetic circuit look like? So I'd have to go around a loop here, right? So I could go around this loop here, let's say, right? If I go around that loop, right? What's my MMF source going around that loop? NS times IA, right? And then how many reluctances do I have there?
2.
Yeah, I mean, you could two is basically what it comes down to, because I've said that the mu of these two materials is infinite. If their mu is infinite, what's true about their reluctance? 0, right? It's basically just, in my mind, what it is it's a wire that guides the flux. It's a conduit for the flux. So there's the R gap on top and the R gap on the bottom. All right, and so if I were to, what do I do with this? I solve for the what in this thing? Yeah, so what's our magnetic equivalent of the current here? Flux, right? And so I would say that phi equals, in this case, NS IA over 2 times the reluctance of the gap, right? Now, typically what I then did was I said, all right, well, what do I do with that information? What's the next step? Flux linkage, which is lambda. So lambda A equals what? That, yeah, NS squared over 2 R gap times IA, like that. And then what do I have for that guy then? I say that I give this a name here, don't I? That's LA. And that's one component of flux, right? What component have I just defined right there? Self-flux. All right, the self-flux. Now, what else do I have to have? Mutual flux, right? So this would be, this guy here is my self-flux. So I'm not done. This would be correct. If I didn't have any currents in B, C, or F, this would be correct. All right, this would be complete. But if I have currents in B and C and F, then this isn't right, okay? So I want to move this out of the way here for a second, and I want to think about what I have in the other coils, okay? All right, so let's think about what I have in the other coils. If I just write out for the whole thing, I'll leave myself enough space here. All right, if I were to write out for the whole thing, I guess lambda A, I'll try to write it here, LA, IA. How do I capture the other coils? How do I write those out? So I would say I have a mutual flux LAB. Yeah, that would be times IB. And then I would say LAC, IC. And I'm going to say LAF, IF.
So if F is DC, is it going to produce a flux?
Yeah, I mean, there's always a flux. And the question is, does it produce a voltage?
Which it wouldn't.
It may. All depends. Let's not, we're not going to rule anything out yet. So there's a step from this, right? In other words, this tells me, just if I look at this equation here, it tells me lambda A equals LAIA. That's what I get from my magnetic circuits. If I want to jump to an electrical circuit model, right? You guys know this is an inductor, right? If I have an inductor and we use the passive sign convention, you would say this is VA, IA goes into the plus sign. This is LA right here. And I have that VA is equal to J omega LAIA, right? That is our circuit model that comes from this thing, right? That's a basic electrical circuit model relationship. And I did this with the passive sign convention. So that stuff's all consistent. In other words, I take the derivative. That's taking the derivative, isn't it? So what I did, I took the derivative in the phasor domain. If I take the d by dt in the time domain, that's the same as multiplying everything by j omega. All right, so you've seen that before with Fourier stuff, and you should be getting somewhat comfortable with that idea. All right, that is my circuit model relationship if I don't have any mutual flux. But if I do have mutual flux, then I have this. And if I want to take this to a circuit relationship, then I got to take the derivative of that whole thing. But before I do that, I want to touch on something we did the other day. I want to figure out what is LAB, LAC, and LAF. Okay. So let's go back to our basic picture of I've got two coils like this. All right. So right here, I've got two coils, F and A, and they're sitting right on top of each other. Okay. And they're oriented in the exact same way. All right. Now what I've done is I've put a normal vector pointing up from the plane of each coil. And this would be a cross section of those coils, right? So A would be coming out and somehow it would turn and it would turn back into the page, right? So this is just a cross section. But their fluxes have this normal vectors here, right? As I've shown it right here, the flux from A through F, all right, is maximized. Basically, the relationship that we learned, so the relationship that you learned in fields was phi equals B dot dA, right? You learned that in fields. And you said if I had a surface, right? So this surface could represent like what coil A is doing, right? Where if I had a current going this way and then that way, right? There'd be a flux going through this surface, right? B dot dA, which is the sum of the total magnetic field passing through that thing. If B and A, if there's those two things are not functions of space, then we said this guy becomes BA times the cosine of the angle between them, right? You guys should remember that basic relationship, right? And so if I talk about the total flux linkage, it's N times that, where it becomes this NBA relationship, right? NBA times the cosine of phi. All right, so in this particular case, where I've got these two coils, right? So I'm talking about basically the lambda in F that's coming from the B field produced by A, right? So the way I define this is lambda AF, right? So this is the flux that's in coil F from the B field in A. What's the phi here in this case? 0, right? Their two normal vectors are totally lined up with each other, okay? So it's maximum. So what I would say in this particular case is I would write this as M times IA, right? Let me write it that way. M times IA. And I'm going to call M is going to be my term that I'm going to use for the mutual inductance, right? I'm going to call this my mutual inductance. All right. Now it turns out if I did the opposite, basically if I said, what's the flux in A from F? It would be M times IF. Those things are always symmetric like that. All right, they're always symmetric. And I'm going to do that without proving it, but it's not too hard to prove it. Okay. What happens if I did this? All right, so now I've turned F, and in the picture here, the phi is equal to 45 degrees. What would I have then? How would I write that? So here I said it was M times IA. So, and that's the peak value of the flux I could ever have through F from A.
It's the NBA cosine.
Yeah, basically it is. We don't usually in circuit terms, we don't usually think in terms of B fields and areas or whatever. We want to get that into an inductance. But yeah, it basically is to say that NBA cosine of 0 degrees is equal to M. right? I guess I got to be careful about that because somehow I'd have to factor out my current from that relationship. So it's not quite M, I guess. I don't know. I guess it would be NBA divided by I or something like that. It would have to, so in other words, the current's not factored into there. The M times IA would be NBA cosine of 0 degrees. Like that, right? But if I keep the current constant and say I'm not changing the current, right? What would it be here? So this guy right here, what's cosine of 0 degrees? 1. So that whole thing is M. So what is it here? M times what? Shifted, yeah, so basically now it's M times cosine of 45 degrees times IA. Right, so in other words, that says that there's a little bit less flux passing through this thing. The total amount of B field passing through there has been reduced. Right? What's going to happen when I get to this picture? Right? So if you think about the B field for this guy, for A, right, it would be going like this. Be that kind of a picture based on the way I've drawn this. How much flux is going through the F coil now? 0. This is basically M cosine. What's my phi value here? 90 times IA.
Which is just 0.
Which is just 0, right? What about this picture? 180, right? So this would be M cosine 180 times IF, which is to say that this is negative M, sorry, times IA. Okay. So if I think about that rotor coil moving as a function of time, so at t equal to 0, maybe he starts out here, and then sometime later he's here, sometime later he's here, sometimes later he's here. How would I write the flux LAF as a function of position, right? And specifically, I would say that it's, so LAIA, that LA doesn't change, right? Coil A is not moving with respect to itself. That's impossible, right? So if I start talking about the rotor, I would say that this is M times cosine theta R times IF. I'm gonna write IF like that because it's a constant current. All right. Now, this is for a two-pole machine. Without getting too wild about it, I'm going to say that that's P over 2 times theta R, which is the electrical angle. And I'm going to define up at the top that theta R is the physical angle. Physical angle. Okay. All right. So that's what I get for that guy. Now, what about LAB here? So we'll write out LAB IB plus LAC IC. All right. Basically, if you look at where B is, right, relative to A, what's the rotation there between A and B? 120 degrees. All right, so that says that this guy is equal to LA IA. And if those coils are identical, what that means is it basically works out to be LA times cosine of 120 degrees times IB. Whereas this guy right here is my LAB. Okay. So basically what it's saying with that is that the coils are identical, right? LAB just ends up being LA times cosine 120 because there's what's the, think about it, going back to this picture here, right? Lambda is n squared over 2 times the reluctance of the gap, right? So if you think about that, the coils are identical, same number of turns, right? Is the reluctance of the gap different for, no, it's the same, right? It's the same gap all the way around. So basically it just works out to be that LAB is just LA times cosine 120. Now, what would it be if I had coil C there? Yeah, it would be cosine 240. So for that, I would have LA cosine 240 times IC. And then I just have this M cosine P over 2 theta R times IF, like that. All right, now help me out. Cosine of 120 and cosine of 240. What are those? What's the cosine of 120? Negative 1/2, and it's also negative 1/2 for the other one. So basically this guy works out to be LAIA minus 1/2 LAIB minus 1/2 LAIC plus M cosine P over 2 theta R IF. Now, if I'm being careful, I really should now write out the fluxes for all of those things. That would be very boring, right? We could do that. It'd be the same type of approach, right? Well, if I wanted to figure out, first of all, LA, LB, and LC, right? How did we define those? LA, we said, just came from this n squared over 2 times the reluctance of the gap.
It's not
Not gonna be any different. LA, LB, LC, all the same, right? Because they're identical coils, right? What about LAB, LAC, LBC, all those things, all going to be the same, right? So at the end of this whole process, if I go through this, what I end up with is this. I can write this out as a matrix relationship here if I wanted to, or I can expand it out like I did here. So lambda A is those 4 things, right? And I have that LA equals LB equals LC. Those things are all the same. And LAB equals LAC equals LBC equals LCA. What are all, there should be L A B B. So I would say B A L A. There should be another one. CB. Yeah. All right. All those things are negative 1/2 LA. Yes, sir.
Is it not P over 2 for the M cosine?
It is P over 2, yeah. So I took, you can tell maybe I screenshotted this. That's a good catch, by the way. You will see it in certain textbooks where they do P, and certain times they do P over 2. I am defining P as the number of poles. Sometimes people use P as the number of pole pairs. We never talk, I never talk about pole pairs. Usually people talk about a 2-pole, 4-pole, 6-pole, whatever. So I use P as the number of poles. And I'm actually, good catch, and I'm glad you pointed that out, because you will see, if you look in, like I said, different places, they will use P as pole pairs, and sometimes they use P as poles. All right, I will always use it in my stuff as poles. Okay, all right, go through this whole thing, and it's ugly, but I can write out, basically at the end of the day, I wanted to get to the torque relationship. I want to do 2 things here. I want to get to the torque relationship, and I want to get to the currents. Okay, or the electrical circuit. All right, so this is our flux relationships. We got that. That can take me to a circuit. Now, we also learned this whole involved process I'm not going to make you guys go through, where I try to write out, what the energy and the co-energy are, right? So if I go through the co-energy, I get that relationship. Tedious, do some integrals. None of them are particularly hard, but you do them and you get to that, okay? Now, that's just saying I can have any old current, IA, IB, IC. I haven't defined what they are, okay? If I just have that top line up there, how do I get the torque from that energy relationship there? What do I have to do? Take the derivative with respect to what? The position. Derivative with respect to position, right? Because this is when it was a a lateral motion, or it could move up and down, then you took the derivative with respect to x or y. But because this guy rotates, you take the derivative with respect to the theta, right? So in this case, this is what? Do any of these here depend on theta? No. The only thing that depends on theta is the stuff coming from the rotor, right? So what's that work out to be? Given what I have here? Well, I mean, yeah, looking at this here, if I take the derivative of cosine p over 2 theta r, what's the derivative with respect to theta r of that whole thing? Negative p over 2 sine, right? So this guy becomes negative p over 2 m, as I've written this, IF0 times sine p over 2 theta r plus sine of p over 2 theta r minus 2 pi over 3 plus sine p over 2 theta r minus 4 pi over 3.
What about the IA?
Yes, and those are still there, right? I A naught, I B naught, and I C naught are all still there. I A 0 like that. Okay. Now, I simplified that down to here. What do you think I did? I skipped a lot of trig, right? Or as I did the trig separately. What did I do to come down to that whole thing? What do you think I did? Well, IA0, IB0, and IC0 all disappeared. Okay. And I got this capital IA.
The magnitude.
Well, IA is a magnitude, but it assumes what about IA, IB, and IC, do you think? Well, what it did was basically what I put in here was a three-phase set of currents, right? So I put in here a three-phase set of currents with IA cosine omega t plus phi, like that. And, IA cosine omega t plus phi minus 2 pi over 3, right? I put that in there, substituted that. Basically, it's a nasty trig thing, and it comes down to this when I'm all done, okay? And it's constant, right? So that's what I wanted, the torque to be constant. I showed that pictorially with the Lorentz force law and everything. This is what it kind of works out to.
Why is it tau E electrical torque?
And I call it tau E because it's electrical torque. It is, and the reason, the meaning of it being negative in this case is it's what? What does it mean that it's negative? It means that it's acting in a direction opposite to motion. Okay, so if I'm operating this thing as a generator, then I'm spinning it one direction and the torque is trying to slow it down. So in other words, as a generator, mechanically I'm putting power in, and electrically it's trying to slow it down. If I'm in the motor world, it's the opposite. In the motor world, you apply the torque and the mechanical world slows you down. The generator world, I rotate it, and the currents act to slow it down.
Phi, and that's phi.
The phi is basically this phi, which, what do I call that phi? I'm going to get to a generator picture in a minute where I have some voltage sources and stuff. This is my power factor angle. Okay. So, all right, back to this whole thing. So there's all kinds of angles that have been defined. Now I got this phi, this theta naught, and I got phi. Let's say, for sake of argument, let's say phi is equal to 0. Okay. Let's say phi is equal to 0. What is theta naught again? Where did I get that? I said starting angle, right? So theta r equals, I said omega mt plus theta naught, like that. Okay. All right. So I want to visualize this a little bit. Let's let phi equal to 0. So let's make that go away. Okay. And let's say I had this picture. So I got two pictures, this one and this one. Okay. And this one, theta naught's equal to 0. How much torque is this machine making? This guy here has 0 torque, right? And in this particular case, the rotor would still be spinning, all right? This is just showing it where. At what time am I showing this rotor?
This t equals 0.
T equal to 0, or more specifically, t equal to the beginning of a period. The rotor is moving, and at the beginning of every period, it's back to that spot, right? So in this case here, there would be some torque. My theta naught in this particular case looks like it's about 45 degrees. So if I had a 4-pole machine, this would be the maximum torque I would ever get out of this thing. All right, what does this say? It says basically the torque is a function of sine. Okay. That turns out to be a really important thing for stability. If I short circuit a motor, that becomes a problem. Okay. We're not going to talk too much about that piece. All right. Basic thing is that angle, the angle of the rotor relative. That's what this is saying. This is the angle of the rotor at the beginning of each period. So if I use this thing as a motor, I have to have controls to go with it, is what this says. All right, because I have to be able to figure out where the rotor is at the beginning of every period. How would I figure out where the rotor is at the beginning of every period? If you're a computer engineer, you'd be using like a sensor of some kind, Hall effect sensor or whatever, to sense the position of a motor, right? So I would need some sort of a sensor to figure that out. Okay. Synchronous motor is a little more complicated. Synchronous generator is pretty easy to figure out. Let's focus on the synchronous generator. All right. This was our fluxes, except I should have the P over 2 here. All right. What I want to do now is I want to get the electrical circuit model. All right. And I want to look just at lambda A there for a second. All right. So this was a picture. This here is the machine. And this is the machine phase A. What I'm going to do is I want to hook that thing up to a grid. All right. So this over here is the grid. And my grid is going to basically have VA equal to so let's do it this way. VA of T is VA cosine omega T. VB of T would be VA cosine omega T minus 120. And VC of T would be VA cosine omega T minus 240. Like that. Okay. So this is what I'm hooking this guy up to. And this is what I called the other day an infinite bus. What did I said that meant, an infinite bus?
Just your voltage source with no
A voltage source that is infinite, or sometimes we'll say stiff bus, stiff or infinite bus. The term stiff probably makes a little bit more sense because the way I think about a bus is a voltage source. So if I think about any bus, so looking into there, I have a bus, I have a voltage source, I have a line where the voltage should be constant. If this thing is stiff, for it to be stiff, what do you think that means for it to be, quote, stiff? It means that voltage amplitude at this point, right? So the voltage between these 2 points at that outlet never changes as a function of time, right? How could the amplitude at this point never change as a function of time? What would have to be true about this resistance? It would have to be 0. Because if this is an ideal voltage source that itself never changes as a function of time, if this resistance is 0, right? Or maybe I should think of it this way. If this resistance was not 0, if there's a current going through here, depending on that current, the voltage I would see at the terminals would get smaller, right? Like at that outlet right there, if I've got a current coming out of that outlet, the voltage you would see at that outlet would get a little bit smaller, right? And you've seen that happen. Like if your air conditioner turns on in your house, what do the lights do?
Dim.
They dim because they're connected to a non-stiff bus, right? There is current flowing that is causing it to reduce. Okay, so in this case, a stiff or infinite bus doesn't have that. It's just a voltage source. Okay, that's the way we tend to think of the power grid. All right, now the circuit model for the machine, this is the machine phase A. And so I'm connecting that thing up to that, which means I need to figure out d lambda A by dt. All right, so I got to start out with my lambda A. My lambda A was supposedly LA IA plus, we got it out to minus 1/2 LAIB minus 1/2 LAIC plus M cosine P over 2 theta R times IF. Now, you guys know enough that if I hooked up a voltage source to this thing, and that voltage source was a balanced 3-phase source like this, well, what do the currents look like? Well, so they're all the same amplitude. They're all shifted 180 from each, or 120 from each other. And in general, they wouldn't have, if I looked at the phase A current, in general, the phase A current would not just be cosine omega t, right? It has to have a phase shift in general, it has a phase shift from the voltage, right? So I would say that in general, I have a power factor angle, right? So I would have IA of t would be IA cosine omega t plus phi. And they would all have that same phi, right? I don't want to go through and write all that out, get ugly. All right, what do we know is true about IA plus IB plus IC? What is that always equal to in a balanced 3-phase system? 0. Okay, so that means that IB plus IC equals negative IA, right? So if I take this thing right here, okay, and I look at it and I say, all right, well, lambda A equals LAIA minus 1/2 LA times IB plus IC. That's equal to negative IA. I like that because that makes that negative go away, right? And then there's this M cosine P over 2 theta R times IF like that. Okay. So this guy becomes what? If I take those terms there and combine them, what do I get? I get a 3/2 LA IA plus M cosine P over 2 theta R IF. I made that guy pretty simple now. All right. Got a heck of a lot simpler than it was before. Right. This is close to a circuit model. If I want to make an electrical circuit model, what did I say I do? I know my lambda. Take the derivative. Use Faraday's law. All right. Now in this case, what am I doing? I'm doing something a little bit different. I'm basically saying this guy is a generator. In the case of a generator, I have my current flowing out. Okay. So in this case, I'm going to say, and I want to jump this into a phasor relationship in a second, but I want to say that VA of t is equal to negative d lambda a by dt, which would be what? How do I write that for this? That becomes what for this guy?
Times P over 2.
Well, just do the whole expression. So I take the derivative of this whole expression here. So what do I do to the first term? Does LA change as a function of time? No. So this guy becomes negative 3/2. I'm going to give this a name. Instead of lugging this guy around as 3/2 LA, I'm going to call this guy LD, which is, there's a reason why I did D, and I'm not going to go into it. This guy is sometimes called the synchronous inductance. Okay. So I'm going to write it as negative LD IA derivative DIA by dt. What do I do with this character here? What do I do with that guy? Well, let's see. I have P over 2. What was theta R? Theta R was, well, and I'd be careful. It's the mechanical speed plus theta naught. All right. This guy becomes minus, I'm going to write it this way, minus M. Is IF a function of time? No, it's constant. Minus M times IF times d by dt of cosine E over 2 theta R. Like that. And I'm not going to take that derivative just yet. And why don't I want to take that derivative just yet? Because I want to jump over to the phasor domain. I don't like taking derivatives. I'd rather do this in the phasor domain. If I do this in the phasor domain, you guys should know, what do I do to VA of t and IA of t? What do I do to this guy?
Negative j omega.
D by dt becomes j omega, just j omega, right? So basically I have the VA, the phasor, equals negative j omega LD IA. And what do I do with this term here? D by dt cosine P over 2 theta R. Well, that guy is a cosine function of time, right? So he's got a phasor too, right? So basically this whole thing becomes, if without getting too in the weeds on the math, I'm going to say minus j omega MIF, and he's got an angle of P over 2 theta naught, like that. All right. Now, what I want to do is I want to get rid of that J on this thing. I'm going to make, so if I see, first of all, if I say V equals negative j omega L times I, what is that? What does this thing here represent in the real world? What circuit model is that? What circuit element is that? An inductor. Very simple, right? This thing over here, this is going to become a voltage source to me, but I want to get the J out of it. How can I get the J out of that? J is a phase shift. Negative J is a phase shift of how much? Negative 90 degrees. All right, so
Theta R.
well, it was theta R here. Theta naught is a shift. Theta R takes into account the time domain part of it. All right, I'm leaving some of that math out of there. Yeah.
So on the last slide, you had I here. So
Oh, yeah, IF. Yeah. like that. Okay. All right. So that, checking my, yep, okay, good. So instead of putting the J there, I can write this as negative J omega LD IA plus omega M IF with an angle of P over 2 theta naught minus 90 degrees. Like that.
And all the omegas here are the electric.
Yep. And if you go slowly through that math, you'll see that it should have been an omega and not a omega M, because it was a P over 2 times omega M that would have come out when I took the derivative. All right. Now, I want to turn that into a circuit model, right? And I don't like this P over 2 theta naught minus 90, so I'm going to make a definition here. And I'm going to say my definition is going to be, I'm going to come up with an angle I'm going to call the power angle. And there's a reason why I'm going to call it the power angle, which is P over 2 theta naught minus 90 degrees, right? I'm going to make that definition. And then I'm going to draw this circuit model right here. So I had basically VA equals negative J omega LD times IA plus, yeah, omega MIF angle delta. All right. So if I did KVL around this loop, I would get the same thing. All right. So this guy here, EAF of T, right? That guy right there, EAF of T, is represented by this phasor right there. Okay. So this here, if I draw a line right here, this is the generator. This is the grid. All right. A KVL would give me the same relationship there. All right. I want to be careful about this, because one of the things that's going to confuse you guys is RMS and peak values later. Okay. So if I say that, just to be really clear, if this J omega LD IA plus EAF, like that, right? EAF as an RMS quantity. I guess I want to be, if all of these things here are, if these are all RMS, this is not RMS. This is all written in terms of peak values right here. All right, let's just be really clear about this. All of these are written in terms of peak values right here, not RMS. All right. I'll have to probably give you guys a summary of the peak versus the RMS so you can keep it straight. Right. All of those are peak values. Yeah. All right. So I want to understand how this thing applies. So basically I gave this picture last time and I said, all right, this guy here would be my turbine. This guy here is the generator.
The turbine is the source of mechanical.
Turbine is the source of mechanical power. It's a steam plant or combined cycle plant. It would be steam, right? And that would act in a direction to accelerate the thing. So that in this case, torque mechanical would act to accelerate it, and torque electrical acts in the opposite direction to slow it down. All right. So what that means is if I try to put more, if I have a stiff bus, constant voltage, and I'm trying to push more electrical power out, I have to put more steam into the turbine to push it harder. In other words, I need to apply more torque. This guy always moves at a constant speed. So if I apply more torque, I'm going to get more power out. Okay. All right, so how would I use this whole situation, right? So if I wanted to analyze this particular situation right here, let's say I'm saying I got two situations here. So the power, if I'm operating this whole thing right here, let's say I just have let's do an example here. Let's say I have a machine that has a rated power. S rated is 500 MVA. All right. And let's say that V rated is equal to, let's say 13.8 kV RMS, like that. All right. And let's say that this is the line to neutral voltage. All right, to keep this simple. All right. Now, let's say what's going on in this particular case. Let's say that this motor is or this generator, let's say it's a 4-pole generator. 4-pole generator. All right. And it's a 60 hertz grid. All right. And let's say that let's say this guy is operating at 90% rated output. And to be clear, rated power output. Rated power at a 0.92 power factor. Okay. All right. First question I would probably ask is, all right, well, how much torque is being provided to the rotor? How much torque is getting provided to the rotor? All right, so to figure that out, you guys go into the torque equation, but I don't have to. It's a mechanical problem here. If I have if this guy is supplying 90% of its rated power at 0.92 power factor, the way I can figure out the torque is by knowing what the power is and what the speed is. What's the relationship between speed, torque, and power? Power is torque times speed, right? So in this case, I have to put in that it's the mechanical speed, right? This is a mechanical relationship. What's the mechanical speed of this 4-pole machine on the 60 hertz grid? 30 hertz, right? 30 hertz, because the relationship is that omega is always P over 2 times omega M, okay? So in this particular case, 90% rated power, 0.92 power factor, right? That tells me that this guy is operating at what? 0.9 times 500 MVA times 0.92, right? That's my power. That's equal to my torque times, what are the units for omega? Radians per second. So this would be 2 pi times 30. That's how I would figure out my torque. Right? That's how much torque is being applied to this thing. Now, why this is important is I'm talking about a generator. If I want to get more electrical power out of the motor or out of the generator, what do I have to do? If I want to put more power into the grid, let's say, okay, let's say I'm at the nuclear power station, right? And I get a command to increase the power. What do I have to do to increase the electrical power into the grid? I have to put more steam. I got to open up the valves more, right? I got to push more steam into this thing. In other words, first thing I have to do is push the torque up, right? So I have to start on the mechanical end to get anything out more out of the electrical end. If I don't change anything about the turbine, I never get anything more out of the generator power-wise. I can change the Q, the reactive power, but I can't change the P without changing the torque. Okay. So what if I said, all right, well, so we figured out what the So I can solve this to figure out what is my torque, right? What if I was told, okay, I want to change the Q value? What do you think I would change to change the Q value, the reactive power? What would I change to change the reactive power? I don't have to change the torque to change the reactive power. All right, well, yeah, change power factor would change the Q. I can never change the P without changing anything about the torque, but without. What other variable do I have control over in this system? Rated voltage is a fixed thing. I can't change that. Once I'm in operation, I can't change that. So what are the variables I got control over? Let's go back to our picture. Let's look at the electrical side. All right. I don't have control in the real world over what omega is. I don't have control over what VA is. VA is the grid. The grid is fixed, right? I don't have control over the current necessarily directly either. What thing can I easily control? IF. And so I can control, well, I can control one of the currents. I can't control both of them, right? When you guys said the current, I was thinking I sub A, but I sub F is the one thing I have control over. I sub A follows whatever it's being told to do. So and look at my control system picture that I had here, right? All right, there are two things that I can control. One is basically I can control the power into this thing, and I can control the current into that field winding. I can control I sub F here, right? I don't control I sub A. I sub A has to follow whatever the system is doing. The voltage is fixed, the power is fixed, I sub A is going to be fixed. I sub A is an output to this thing. Torque, basically my inputs are torque and I sub F, okay? So if I'm told to change the Q, so to change the power, so a change in power, change in P means a change in torque, a change in Q comes from a change in I sub F. Okay. That's our basic relationship. So this is a sort of a simple example. We'll look at a more, we'll go through a specific detailed example on Monday. But this should be enough to get you through into the first, really into the first, all the problems at this point. Although you may have a little trouble until we get through some examples on looking at 4 and 5.
What happens whenever, you hear about generated